depending upon zeta values, we have different types of responses of second order system. So zeta is a damping ratio. Depending upon the damping ratio value, we'll have different types of systems. Responses. What are the responses we'll see? First we'll take zeta is equal to 0. When zeta is 0, you look at the characteristic equation. It is actually s square plus 2 zeta omega ns plus omega n square is 0. So when you substitute zeta 0, then it results in s square plus omega n square is 0. So what are the two roots? S1 comma S2 are plus or minus j omega n, which means I have two poles or two roots on the imaginary axis. Then if you take explain here, one pole is on imaginary positive side, another pole is imaginary negative side, and its value is omega n and as well as omega n. Means system will have continuous oscillations with a frequency of omega n. Means system will be at a verge of instability, system will be at marginally stable, something like system will have continuous oscillations. So when zeta 0, so this kind of response we will get. Now we'll see that response. Now this is x-axis time and this is t, and what will be the steady state value? Let us say this is your unit step response, and for unit step response the steady state value is 1. So this is the steady state value. Now if you increase the time, right, the moment you apply the step input, if you increase the time, the response will have continuous oscillations as it's shown here. We have continuous oscillations and those oscillations are sustained. We have continuous, and the magnitude of oscillations is not changing. We have constant oscillations. So this kind of response you will get when zeta is 0 and my poles or roots are purely imaginary. So it is called undamped response. What do you mean by that? So damped means a force against the oscillations. Damped means we have some opposition force to oscillations. Undamped means there is no opposition force to the oscillations. Hence, oscillations can exist for longer time. Even if you take t is infinity, still we have oscillations. So this is what your undamped nature of the system when zeta is 0. We'll take another case when zeta is slightly increased, means that the zeta value is from 0 to 1. So when zeta is 0 to 1, look at the characteristic equation. Your q of s is s square plus 2 zeta omega ns plus omega n square is 0. What are the roots? S1 comma S2 are minus zeta omega n plus or minus j omega n into 1 minus zeta square under root. So if you look at S1 and S2, both are having the real part and imaginary part. So whenever you are having a real part and imaginary part, and these pole locations are called complex conjugates. So S1, S2 are the complex conjugates, real and as well as the imaginary. What will be the real part? It is a zeta omega n minus zeta omega n. Both are in the left side and the location will be minus zeta omega n on the real axis. Imaginary omega n into under root 1 minus zeta square. Now I can define another frequency which is called damped natural frequency. We have one frequency omega n. What is omega n? Undamped natural frequency. That means when the system is at undamped, the frequency of oscillations is omega n. Now in this case we are taking another term, frequency, that is omega n into under root of 1 minus zeta square. So it is called omega d. So omega d stands for damped natural frequency. So undamped means there is no force against your oscillations, so oscillations are continuous. Damped means yes, there is some opposition force to oscillations, therefore the oscillations are going to be die out after some time. And at what frequency the oscillations are going? the oscillations are going with this frequency omega d. Therefore, the locations of S1 comma S2 are minus zeta omega n plus or minus j omega d. Now, take these two poles and locate an S-plane. This is my S-plane, real and imaginary. And this length I can take zeta omega n, and this length is omega d. Therefore, there exists a one complex pole and another complex pole. We know that the complex poles are always in pair. Complex conjugates are always in pair. Even imaginary also we have always in pair. So one pole here, another pole here. The kind of the response we get with these poles for any step input is called underdamped response. So it is underdamped response, means the enough damping is not there, still lack of damping. So that is the reason why we have oscillations exist, but fortunately those oscillations are going to die out after certain amount of time, that is in transient period oscillations are there, in steady state period oscillations are died out. Now, so underdamped response is like this. Next is we will take zeta is 1. So when zeta is 1, it is called critically damped system. So critically damped means we have enough damping available. Zeta is 1. Again we can write the Katsky equation, s square plus 2 zeta omega n plus omega n square. Zeta is 1, therefore s square plus 2 omega n s plus omega n square is 0. So this we can simplify it as s plus omega n whole square is equal to 0. Means there are two poles, two real poles in the left of the S-plane. S1 comma S2 is minus omega n, again minus omega n. So there are two poles which are existing on the negative real axis, and the location of the poles I can say two poles are two roots of the Katsky equation are equal and as well as the real and equal, but they are in the left of the S-plane. Now since the damping is enough, there are no oscillations at all. When you look at the response will be directly rises like a first order response, it goes to the steady state value. In this case steady state value is 1. So your critically damped response is almost similar to your first order response. Critically damped means enough damping is available to the system. Now root locations also we said. Next, overdamped system. So overdamped system will have zeta is greater than 1. It is greater than 1, it can be any value from 1. So it can be taken as 1 to infinity, say. So greater than 1 zeta value we will call it as a overdamped. What do you mean by overdamped? You have taken more care about the damping in a system. So when you take more care, then we call excess damping is available. When excess damping is available, basically damping is damped means we have opposition to the oscillations. So we are taking more care about the oscillation. The system will not allow to this damping factor will not allow you to reach the steady state value. Slowly it increases, it takes longer time to reach. So such kind of systems are sluggish in nature. If you take more care about the damping, they are sluggish systems. Then if you look at again Katsky equation, s square plus 2 zeta omega n s plus omega n square is 0. Then the roots will be s1 comma s2 is equal to minus zeta omega n plus or minus omega n into under root of zeta square minus 1. That means both the poles are real only, but they are not equal, they are unequal. So the roots are real and unequal, and you can locate in S-plane. I have one pole here and another pole here. One pole is going nearer to the origin or imaginary axis, another pole is going towards the minus infinity. So out of these two poles, now which pole is responsible for the sluggish nature? We know already in S-plane, if the pole is moving away from the origin, then your system will have faster response. Then the pole is moving towards the imaginary axis or towards the origin, then that pole will have very high time constant, then that is the responsible for sluggish nature of the system. So even if you have pole here and a pole there, then the pole which is near to the imaginary axis or origin will have more dominant than the pole which is going away from the imaginary. So the pole here at minus infinity will have very less effect. I can call it as an insignificant pole. The pole which is nearer, which is going nearer to the imaginary, which is called dominant pole. So out of these two poles, the pole which is there is responsible for the sluggish nature of my overdamped system.